So, T-duality. In string theory, you need 26 dimensions of spacetime because otherwise the theory is not Lorentz invariant. So we need 25 spatial dimensions. And as we see around us only 4 dimensions, there should be something special about other dimensions. For example, they can be compactified. And the simplest example of a compactification is Kaluza-Klein compactification. That means that if we have, for example, just one compactified dimension, this dimension is not infinite in spatial extent, but it is finite. It is, in Kaluza-Klein case, it is compactified onto a circle. So one of the dimensions is a circle, and therefore it's finite and compact. What happens with strings that live in a world with compactified dimensions? If we just consider just one compactified dimension again, and suppose it is compactified on a circle, then we can calculate the embedding functions of strings, meaning the functions that embed the strings in our spacetime. If we write them down, these functions, then we can calculate mass squared of a particular excitation, because in string theory, particles of different masses arise from different modes of excitations of a string. So suppose we consider closed string. A closed string is such that it starts and ends in one point. Obviously, it should satisfy a periodicity condition, namely, if I walk along a string, if I run along a string distance equal to 2 pi r, or 2 pi r times some natural or some integer number, I should go back in the same point, because if I walk 2 pi r, I get in the same point, and I can do this several times. So I can write the periodicity condition as x of some sigma, where sigma is the coordinate along the string, x of sigma plus pi, because in string theory on closed strings you impose periodicity of pi. I mean, the sigma of pi gives you the same sigma. So x of, I think that's right. X of sigma plus pi is equal to x of sigma plus 2 pi r times w, where w is the winding number. It is the times, how many times I went around my compact dimension. So then we can calculate the mass of, one more thing about the compact dimension is that the momentum will be quantized. The momentum along this compact dimension would be quantized, and you can write this down as something proportional to k over r, where r is the radius of the compact dimension and k is the Kaluza-Klein excitation number. It's basically like if you have some momentum, how much is it in terms of the quantum of momentum along this dimension. So you can write this down. You can calculate the mass squared of the different modes, and you can find that very interesting result. If I change k, which is the Kaluza-Klein excitation number, and that is associated with momentum, if I exchange it with the W, the winding number, how many times I walk along around the compact dimension, if I exchange them and also make a change such that my radius of compact dimension goes to alpha prime over r, so r goes to alpha prime over r, well, where alpha prime is proportional to 1 over tension of the string. If I do this change simultaneously, k and omega interchanged, and r goes to alpha prime over r, I have the same result. The physics then is exactly the same. So if I have compactification with radius r, with the winding number W and Kaluza-Klein excitation number K, and if I have another theory in which the compactification radius is alpha prime over r, and where omega and k are interchanged with respect to the first case, then these theories are the same. So in a sense, if I, for example, consider in my first theory, I can say that different Kaluza-Klein excitation numbers, that they correspond to different particles. In my other theory, I would say my different winding number correspond to different particles, and different K's correspond to, yeah, it's not really clear what this means, because okay, in the first case I have some, well yeah, so if in one case I go around my compact dimension and that changes the mass of some modes of some particles, in another case that corresponds to exciting momentum. But in the first theory, exciting momentum corresponds in the other theory to going around the compact dimension. That's quite interesting. So this is the T-duality, and there are more complicated dualities. Another thing which is interesting has to do with the boundary conditions. So there are, if I have, and this has to do with open strings. So open strings don't have winding number because they are topologically an open string. You can shrink it to a point, so you can't really talk about winding an open string around something. But if I write down an equation for embedding function for an open string, and then I consider this T-duality thing, so I do exactly the same, I exchange the same things, then I get the equation, and also in the first case I impose von Neumann conditions. So von Neumann conditions say that the derivative of the embedding functions at the ends of the string is 0. This has to do with conservation of momentum. So it's like if I have a string, then it can do anything it wants in the middle, but at the ends the derivative, it should be flat. It should not go like that or like that. So this is von Neumann conditions. But if I apply the duality transformation, I get Dirichlet conditions. So these von Neumann conditions in the first theory, they correspond to Dirichlet conditions in the other theory. And Dirichlet conditions, they say that endpoints of the string are fixed. So it's not about the derivative, but the points themselves are fixed. It's quite interesting. It is really weird how you can get Dirichlet conditions from, I mean, it's not you get them from von Neumann conditions, but von Neumann conditions in one theory correspond to Dirichlet in another theory, which is weird. Yeah, it's quite weird.